Okay, welcome back everyone. In section 6.1, we defined what a normal distribution was, and we did mention its continuous probability distribution, and we did mention that in order to find probabilities, we need to find the area under the curve. However, we never looked at an example. We just basically mentioned about the curve and some of its properties, such as the symmetry of the distribution and the tapering of the distribution rather rapidly. And we also talked about a standard normal distribution, which also is called a Gaussian distribution, by the way, in honor of Carl Friedrich Gauss. So in this section, we're going to actually look at how are we going to find the area under this curve. Now, in order to find the area under the curve again, we can use a table in the back of the book, which I show you, and then we can use a statcrunch. Now remember, we would really like to use a statcrunch for what we do because it makes our lives a lot easier. So let me actually make up an example here. So in our example, here's what I want to do. Let me move this to the side, and we're going to use this pen. So let's say I want to find what is the probability of a z less than or equal to 1.35. So I just made up a statement here. Okay, so I want to know what is the probability of a z less than or equal to that. Now, if I draw the distribution, if I draw the curve corresponding to this, okay, and let's see. So if I look at the normal distribution, again, we look at the standard normal distribution corresponding to this. It's going to look something like so. And what we often do is the following. Under this normal distribution, here's the label of z. And what we often do is we actually draw the area that corresponds to this probability. So remember, the normal distribution, standard normal, always have center the mean at 0. So this distribution is normal 0, 1. That's what this distribution is. Okay. Now, probability of a z less than or equal to 1.35. Again, remember that the horizontal axis is a number line. So 1.35, that's about 1 deviation, 2 deviation. 1.35 is roughly about here, somewhere in here. We're going to call that 1.35. Now, the area that's to the left, that lies to the left of this, corresponds to the probability statement on the left, that is over here. That's what this translates into. So, in order to find this area again, we can go to a table in the back of the book. So I'm going to use table 2. It's in the appendix, table 2. That's Roman 2, table 2. And let me go to that table and actually show you what this table looks like now. Table 2, and let me go to, there you go. This is the page of the book. This is the section that we're talking about right now. And I want to go to table 2. Now, table 2 in the appendix, if I remember the page number, and I've done this so many times that I have the page number actually memorized, it's page AP, I believe it's dash 6. Let's see what comes up. Hopefully that's the right table. Now the table, once it loads, the table, yeah, it is. This table appears on 2 pages, AP6 and AP7. Okay, so let me go to, first of all, AP7 here, maybe easier to start with. So, the way this table is constructed, by the way, the way this is done, is that along the top row, right in here, top row, these are the second decimal in a z-score. And along the vertical margin here, these are the z-scores also. So the margin of the table, that's again the top, and the left margin, the left column, this is the margins of the table. The numbers that are in here, this is called the body of the table. So inside the body of this table, you're going to see these numbers. These are actually probabilities. Okay. Now, and to the left, there's a drawing. Notice this is a standard normal curve. That's what this is. And in this drawing, there's a shaded region. Now, the shaded region is to the left of a z-score. So the z-score is the number that we're working with. In my example, z-score is 1.35. So if I locate the z-score 135 for my example, I go along the column 1.3, so that's where that is, and then the 5, that would be the hundredths in 1.35, the hundredths, that decimal is 0.5. So I go to the column 0.5. Now if you go down the column and across the row, here's 1.30, and you go up here 5, so 1.35. There's a number that sits right in here. This number is 0.9115. Now, what is this number? The author of this book, he pledges that he's going to give us the area to the left, and always to the left in this book, always to the left of a z-score, not to the right but to the left. So when I look at 1.35, the number 0.9115, that number is going to be the area to the left. Again, that number is 0.9115. That's the area to the left. So this is in effect what we just found. There you go. And that number is 0.9115. There. Very simple. And that's how we're going to use the table. Now, we're not going to need separate table for areas that lie above or between two z-scores. Remember, he only gives us the area to the left. Now, let's say, for example, we want to find the probability of a z that's above 1.35. Notice it's just the opposite of what the author is going to give us in his table. So in order to do this, what I can do is the following. I can say, well, if the area to the left of 1.35, if the area to the left of that, that's this area to the left, is 9115, the entire curve, the area under the entire curve, that's from negative infinity to infinity, is 1. So we can actually be a little creative here, and we can, let me highlight this for you. I hope this works. And there you go. This is the highlighted portion. Oh, sorry, that's my highlight, and there's my pen. Okay, so I can actually highlight this for you. There you go. This area, this is nice. This area is what we want. So this would be the yellow highlight is what we're looking at. So I can find that area by doing 1 minus 0.9115. And that number is going to be 0.0885, which is about 8.85%. So a probability of a z-score greater than that is going to be this. Let's call it 9%. Now, let's do another example. Let's say I want to find probability of a z-score that lies between 0.76 and 1.24. I'm going to put equality on one and not on the other, and then I'll make a comment about having the equal sign or not having it for a continuous distribution. So now let's draw the standard normal distribution that corresponds to our probability statement. So here's my normal distribution, center at 0. 1.24, that's about here-ish. And 0.76, let's call this one to be 0.76. So this is actually the area that we want to find. This area corresponds to the probability statement to the left of it, over here. Now, in order to find this, what we could do is we can do superpositioning of one area over another. And here's what I mean by that. Let's say I'm going to take a look at the area that lies to the left of 1.24, and then I'm going to look at the area to the left of 0.76. Now remember, anything to the left of 1.24, that area, that means from 1.24 all the way down to negative infinity. But we don't need all of that area. We only need that, what you're looking at, this sliver that you're looking at here. This is what we want. So I'm going to go back to our table and remember the numbers, see if I can memorize them. It's 1.24 and 0.76. I actually jotted down the numbers. So there you go. I'm going to go back now to our table, and there you go. So this time I'm going to look at 1.24. Here's 1.2, and the 400ths in 1.24 is this column, and you go down the column over to the row projected to the left, and if I'm looking at the right number, this is 0.8925 right in here. So I'm just going to write this down before I forget it. 0.8925, and then the area to the left of 0.76. I'm going to find 0.76. So here's 0.7, and the 600ths go right about here. And if I project up to the column, that's 0.6, and 0.7 is in the middle. So this is roughly where the whereabouts of that is. There you go, 7764, and that's 0.7764. And I wrote that down on my paper again. And now I'm going to go back to my note, and I'm going to transfer these numbers. So first, the number to the left of 1.24, this one, was let me move my cursor in the corner so it won't disrupt you or disturb you. So this is 0.8925 is what I found, and to the left of 0.76, this number was 0.7764. So what we're going to do is now we're going to do a little bit of arithmetic here. If I take 0.8924 and subtract from it 0.7764, that's got to be the number that we are looking for. I'm going to use my calculator on this one. 0.8924 subtract 0.7764 from it, and I get 0.116. Okay, so that's about 11.6%. There you go, and that is the probability of a number that is between. So note what we were able to do in the beginning. The first example I have up here, right up here. This one we're able to find probability of something that is less than or equal to. That's this one, less than or equal. We can find. We can also find probability of greater than, and now we are able to find probability of between the two. Okay, and we'll find these probabilities, by the way, when we go to statcrunch. I'll show you how it's done really easily in statcrunch. So let me write the less than 1.35, greater than 1.35, between 0.76 and 1.24. So when I go to statcrunch, I know what to type in. Okay, so hopefully everybody's good so far, and this is how we can find these areas. That means probabilities. Now, I want to mention something about having or not having an equal sign. Okay, so let's say this is now a separate example. So in this example now, we want to find probability of a z exactly equal to 1.2. Now remember, the table in the back of the book gives us less than or equal, not exactly equal. But this is what I want, exactly equal. So the key is this, exactly equal, right in here. Now, if I translate into what I have, this probability statement, if I translate the probability statement into an area under the curve, under the standard normal distribution, so this is going to be the z-axis. And here's my normal distribution, let's say. There you go. I know the tails sit up here quite a bit. It shouldn't really be like that, because again, they taper rather quickly. So that's okay though. Let's not the point of what I want to make. But anyway, there you go. A little better now. Okay. Now, in this one, let's say if I want to find probability of z exactly equal to 1.2, so this is again where 1.2 is, right? So the problem amounts to finding the area under the curve. Well, under the curve, I have a line. So I guess it begs the question, what is the area of a line? Now, we know a line has length, but has no width. That has to do with the Euclidean definition of what is a point, what is a line, and so on. So a line, turns out, has no width. It only has length. Therefore, because there is no width, so it has no area. So in other words, the area of a line is 0, which means probability of z equal to 1.2 is going to be equal to 0. And there you have it. So that's what we got to deal with. Now, the consequence of this, however, it's interesting. It's consequence, what it's going to do for us. So here's what it means for us. If I want to find probability of let's say something I've done up here, z greater than 1.35, it's right up here. Something we've already done, we have the number, the answer. So if I change that to a probability of a z greater than or equal to 1.35, again, notice the way I read this statement is greater than or equal to. The keyword here is or. And based on the way we read this statement, that's probability of greater than or equal to 1.35. Now, probability of exactly equal to for any number, any z-score, is going to be 0. So this part of it is 0. That probability is 0. So what this means is that probability of greater than or equal to is going to be exactly the same as probability of z greater than 1.35, and that was something that I found up here, 0.0885. 0.0885. So there you go. That number isn't going to change. So keep in mind, whether you include equal sign or you forget to include it, whether the problem requires it or not, it's not going to affect the probability. Now, to be correct, we need to correctly write the statement, but in our computation, having or not having an equal sign doesn't make a difference. And in fact, this is true for all continuous probability distributions, not just for the normal distribution. So, hopefully you follow that part. Now, what we want to do next is this. We would like to go to table. Actually, let me go back to that table. I'm going to make a different probability statement, then we go to statcrunch. Here's another example. What if I have a negative z-score? Let's say I want to find probability of a z less than negative 0.36. There you go. Notice it's a negative score. Well, that table that we went to, it comes in 2 pages, as I mentioned earlier. So here's table on page AP7. If you go back to AP6, now here you're looking at negative z-scores. See right in here? These are negative z-scores. This author chooses to have area under the curve, always to the left of the curve, for z-scores as little as negative 3.9 and all the way up to, if I go to the next page, they go up to, there you go, they go up to 3.9. So he covers almost 4 standard deviation on either side of 0. Now, if you notice, numbers above 3 deviation do not change much, and that's because the distribution has tapered on the right side. If you look at the left tail, that's table AP6. Numbers to the left of negative 3 aren't going to change much because the distribution has tapered on the left side over here. So there's not much going on there. Okay, Now the example I had, forgot what I had. I think it was negative point. Let me go back and check it out. Negative 0.36. Okay, so if I go negative 0.36, oops. Okay. The reason I say oops is because I need to scroll down. This is where negative 0.3 is. But the 600ths in 0.36 is up here, and when I scroll, I'm going to lose a column. So here's 06 in 0.36. That's the 06, the second decimal in number negative 0.36. First, second, third, fourth column from the left. There we go. So I'm going to go negative 0.3 and 1, 2, 3, fourth column from the left. This is where the number should be 0.3594. 0.3594, and I'm going to write that 0.3594. There you go. 0.3594. That's where that is. So that's how we find the area to the left of negative numbers. Now something that does come in handy, as we're going to look at later, when we look at these things later on, is the following. Let me draw the area that corresponds to this. So here's the normal curve, again a standard normal distribution. This one looks a little better than my previous one. Okay, so here's 0. Now to the left of negative 0.36, that's negative 0.36. The area to the left of that is right about here. And that area we found it to be 0.3594. Now note, by the way, there is no correlation between the number here and the number in here. They just so happen that they're pretty close. Yeah, maybe I should have picked a different number. But remember, the z-scores can be above 1. They're from negative infinity to infinity theoretically, but usually your z-scores probably lie between, I don't know, negative 4 and 4. Could be anything. But the point being, the probability, that's what we're working with here. Oops, sorry. There. This is a probability right in here. This probability has to be between 0 and 1. So the answer to this probability question, this must lie between 0 and 1. But the z-scores, these are z-scores. These can be anything. Okay, so just want to point that out, because these two numbers are awful close, although this is negative, the other positive. But anyhow, now here's what I want to point out. So now that we have this, what if I want to find probability of a z greater than 0.36? This is now a positive 0.36. Now, by symmetry, if I draw the distribution, the area under the distribution, this is 0.36, and this is what we want to know, right? We want to know what is this area. So you can kind of see by symmetry of this distribution, there, I'll make it a little more symmetric. No, I'm messing this thing up. Oops. There you go. I was going to get an eraser. So there, shaved it off a little bit. Okay, so by symmetry of this distribution, I can say the area to the right of 0.36 is exactly the same as the area to the left of negative 0.36. So again, due to symmetry, I'm going to say the answer to the question mark is 0.3594. It will be exactly the same, 0.3594. And there you have it. Now, these probabilities, we can find them in statcrunch. So again, I've kept track of all of these as I wrote them down on this on the screen for you. Less than negative 0.36, greater than 0.36. I just added that to my notes, and greater than or equal to 1.35. And with that, we're going to go to statcrunch. Okay, so there you have it. Now, let me go to statcrunch. Okay, Now in statcrunch, here's my, let me see if I have that. No, I don't. So I'm going to click on statcrunch and data set from your textbooks. And here we are in statcrunch. Spin, 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 and there it is. Okay, now here's where we go in statcrunch, trying to find those probabilities. We're going to go to stat, then we go to calculators. Now remember, this is a probability calculator. It's not like your TI calculators or any other calculators that you were used to. So we've already used this calculator for the binomial distribution. So all I'm going to do is just go down to alphabetical listing, and there you go, normal distribution. Click on the normal, and by default, you're going to get this nice looking symmetric distribution. So again, if you look at this, tapers to the left, tapers to the right, here's the center, and it's nice symmetric. Now the default in statcrunch, it gives you mean 0 deviation 1, and that's exactly what we want in section 6.2. We want the area under standard normal curve. Now if you look at here your options, for one thing statcrunch calls it X, we're going to call it Z in section 6.2 because we're working with Z scores, but that shouldn't confuse you, I hope. But if you look at here now, we have the choice of less than or equal or greater than or equal to. Notice there is no less than or there is no just greater than. And that's because of what I mentioned earlier. It doesn't make a difference whether you put equality in that inequality or not. Whether you put the equality or not makes no difference. The direction does make a difference, but not whether you have the equal sign. So let's say we want to find probability. Our first example we had, I believe, probability of less than 1.35. So I'm just going to go here and type 1.35. Okay, and there you go. So that probability is going to be 0.91149. Now, on the table that we use, the author's table, he rounds his probabilities to 4 decimals. That's the nearest 10,000ths. Obviously, for space restrictions, so it's got to be limited to a finite page. But in statcrunch, it displays it to 8 decimals. And I believe behind the scenes, it actually carries double precision, means up to 16 digits. So they will be off somewhat. But anyway, that's pretty close to what we have. And then the other example we had was greater than. So if I change this to greater than or equal, and you get the number we had is familiar, 0.0885, and notice how it paints the area to the right, so you know exactly what the shaded area corresponds to that probability statement. Now, if you want to find the area between, you go up here, you click on between, and the default is -1 to 1. The -1 to 1, by the way, that's 1 deviation above, 1 deviation below. I didn't mention this, but there is a rule called empirical rule. And I'll write it down for you later on before the end of this section. What the empirical rule says, the word empirical means based on actual data. Empirical rule says if you go 1 deviation above, 1 deviation below the mean, the region that you see here in red covers about 68% of all scores. And you can kind of see that it's more exactly 68.27. So, but the empirical rule rounds it to about 68%. Same rule says 2 deviations. I'm going to mention these and then we verify them later. I write them down for you, not verify them, but write them down for you later. This one, I'm going to go -2. Okay. And then this one, we're just going to type 2. Now I'm looking at 2 deviations above and below. Okay, and you can see 2 deviation covers about 95.4%. That's 95. Over 95% of all scores are only 2 deviations. Although theoretically the distribution goes from negative infinity to infinity, but there's not much left there. Let's change these numbers to negative 3 and 3, and you'll see something interesting. So that's negative 3, and let me put 3 here. Let me bring up my keyboard, and this is gonna be 3. Ooh, 23. Ooh, that's too many. Okay, let me go back. I forgot to backspace. 1, 2, and that's gonna be now 3 deviations, and there you go. Compute, and you kind of see that the entire distribution now almost is in red. 3 deviation above below covers 99.7% of all scores. There's not much information left beyond that. So again, theoretically, this goes from negative infinity to infinity. But anyhow, now I want to do one last one. So this is between. You can find betweens like that. We did a between in our examples. Let me actually do that between. We did between 0.76 and 1.24. So I'm going to go between 0.76, enter, and this number was 1.24. So I'm going to go 1.24, enter, and there you go. The number we had was pretty close to that, 1161, and there you have it. So you can see that's between, and you can see the, again, shaded region. Now let me go back to standard, and let's do our last 2 examples that we did on paper, paper. That was to the left of negative 0.36. So I'm gonna go, this is negative 0.36, and that's gonna be 0.3594. That's what we had, 0.3594. And the area above 0.36, we're just gonna change the negative sign to a positive sign and change this to greater than, and you can see exactly the same area, 0.3594. So with this, we're done with section 6.2. Again, in 6.2 we wanted to know how we find the area under the normal distribution. Now there's one exercise I like to do with you in this section that's going to be very useful, and we're going to do this exercise. We're going to actually take a look at this exercise. Let me bring up the page again. We're going to be using this exercise later on as we go through. So we're in chapter 6, and multimedia textbooks, find now, section 6.2, area under distribution. The exercise is on page 269, but before we do the exercise on page 269, let's go to page 266, and that's the page that I'm going to go to. On that page 266, we're going to use a notation, something that we will do throughout the future chapters, especially in chapter 8, 9, and beyond. So let me backspace, and I'm going to type page 266 here. Okay, and this notation is the Z subscript alpha notation. There we go. This is the notation, the Z sub alpha notation. And of course the author describes what it is. A Z sub alpha means find a Z score right in here, so that the area to the right is alpha. This thing that looks like this, it's Greek alpha. So that's what this is. Alpha is going to look like what you see on the screen here. This is what alpha is. So let's actually look at that exercise, and I'll explain how to do this exercise, finding area to the right. I mean a Z-score for a given area to the right. This exercise is on page 269. Okay. And it's exercise number 79. And there you go. This is the exercise right in here, number 79. It says find z of 0.1, which we already found, for example. Then we want to find z of 0.5, 0.25, 0.1, and 0.05. Now, I'll do all of these on that OneNote for you, but let me again copy these numbers so I can duplicate them in my OneNote. Okay, so we're going to answer these questions. Now, I'm going to use the statcrunch to find these numbers, okay? Because it's going to be a lot easier. Now, here's how we're going to do this. We're going to go to statcrunch. Where are you? Statcrunch. Right in here. And here's the statcrunch. Okay. Now, I want to find the first number, z of 0.1. Okay, so z of 0.1. I go stat, calculators, and normal distribution. Now, usually we put a z-score here and find the area above, below, right? Because we're doing the z sub alpha. I want to find the area to the right. Now, in here, I'm actually going to type the area that we are interested in. That area is going to be 0.1. Okay, 0.1 means 10%. This red region, the highlighted in red area region under the normal curve on the right tail is 10%. The z that corresponds to that is 1.28 rounded to the hundredths, and that's what the author had. Now, let's change that to 0.05. So we're going to make the area a little smaller. Okay, a little smaller. So I'm just going to go back and change it to 0.5. Okay. Compute. Notice the area is getting smaller. The probability is getting smaller. And consequently, the z-scores are getting bigger. So the z-score for this we're going to use is 1.645. Okay, I will write these down on my OneNote in a few moments. Let's change this area now to 0.025. Okay, so I'm going to go back, 0.025. And now the area 0.25, again, notice the red highlight is getting smaller, the area is shrinking, but the z-score is getting bigger. That means we are pushing into the tail end of this distribution. We're going to go with number 1.96 for this. And let's do yet another one. This time we're going to do 0.01. So the number is going to be 0.1, enter. And oops, I meant 0.01, sorry, no biggie. Let me just go 1, enter. There you go, 0.01. For this, we're going to go 2.326. 2.326. And finally, 0.05. Notice, by the way, 1% area on the right, the area is ever slightly smaller than the previous one. Now, at 0.05, that area is going to shrink significantly, right? It's going to be even smaller area. Because again, we're looking at this smaller region in the tail. So 0.05, and I'm going to go back, and this time I'm going to put 0.5, enter, and there you go, 0.05. Look at that tiny region in the right tail. So the number we're going to go for this is 2.576. 2.576. And with that, we're done with use of statcrunch. We're not going to use statcrunch in this section anymore. I'm going to go back to my OneNote, and we're just going to write these now down. So here's what we got. First, the z sub alpha notation. This is a z sub alpha. Remember, alpha is a Greek alphabet. There you go. And this is what alpha is. Right? Okay. So a z sub alpha means this. If I draw the distribution, normal distribution, and this is a z, so the center is 0 deviation 1, right? That means a z-score, so that the area to the right is alpha. Now the z's here that I have, by the way, this one is capital Z. This is the name of the variable, whatever z is. This should be little z actually, so let me make it little for you. There you go. So that's like little z. So this is cap Z, that's little z. There is a difference between them. Capital Z is a literal variable, means letter. Little z is going to be a number for us. Okay, so that's the distinction between them. Now, so here's what we're going to write down. We're going to say z of 0.1 is 1.28. We're doing that exercise now. A z of 0.5, we're going to go 1.645. A z of 0.25, we're going to 0.25. There you go. Let me correct that. Z of 0.25, that's going to be 1.96. And a z of 0.01, that's going to be 2.326. And a z of 0.005, that's going to be 2.576. Now, these z scores, we're going to use over and over again. So, nice rainbow colored border for you. The z scores, we're going to use them again. So now that you have them here in section 6.2, we're going to be able to reuse them later on. Now, we're going to finish this section shortly. Let me just put that empirical rule that I mentioned about. The empirical rule tells the following, that if you have the interval mu plus minus 1 standard deviation, that covers approximately 68% of all scores lie in that interval. The interval mu plus minus 2 sigma, that covers about 95.4% of all scores. And finally, 3 sigma covers 99.7% of all scores here for us. And with that, I'm going to end this section. Okay, thank you all.